Okay, this is section 14.4, the colligative properties of solutions. We're going to describe what we mean by colligative properties, identify four colligative properties of solutions, and we're going to do a little math here, determine the boiling point elevation and freezing point depression. So raising the boiling point and lowering the freezing point. And the vocabulary is all these things: colligative property, vapor pressure lowering, boiling point elevation, freezing point depression, osmosis, and osmotic pressure. And the main idea is that colligative properties depend on the number of solute particles in a solution. Okay, it doesn't depend on what is in solution. Okay, it just depends on the number of particles in solution. It can be salt or sugar or glucose or anything that can dissolve in water that's non-volatile, that doesn't, evaporate away. So it doesn't depend on what is dissolved. It only depends on how much of that substance is dissolved in the solution. So colligative properties, again, restated, are physical properties of solutions that are affected by the number of particles, but not the identity of the dissolved solute particles. So like I said, you'll get the same properties whether you have the same amount of sugar dissolved, salt dissolved, um, different things dissolved would be the same thing. And ionic compounds create electrolytes because they dissociate in water to form a solution that can conduct electricity. So that's kind of a review. And some molecular compounds are also electrolytes because they have polar properties on them. Electrolytes that produce many ions in solution are strong electrolytes, and many molecules do not ionize when dissolved and do not conduct electricity. Okay, so kind of a view of what ions were there. Adding a non-volatile solution to a solvent lowers the solvent's vapor pressure. So non-volatile solute is something that's not going to, it's going to dissolve, but it's not going to evaporate. It doesn't have it's not a gas or liquid. When this solute is present, a mixture of solvent and solute occupies the surface area and fewer particles enter the gaseous state. So it makes it harder for the particles, the solvent particles to go into the gaseous state. And the greater number of these solid particles, it lowers the vapor pressure over that. Remember that boiling point was where the vapor pressure of the atmosphere equaled the vapor pressure of the liquid. Well, if it lowers the vapor pressure, that's going to take more kinetic energy to create that same vapor pressure we had before. So if we just have water and we dissolve sugar in it, it's going to take that more, there's going to be less water molecules above in the vapor pressure here in the gas above the water here than there would be normally. So the sugar molecules inhibit the evaporation, or makes the vapor pressure lower. It makes it harder for these molecules to go into solution. To go into gaseous state. Okay. When it lowers the vapor pressure, the boiling point also is affected because more heat is needed to apply more kinetic energy to get the vapor pressure to equal the atmospheric pressure. And that's the definition of what boiling is, when the vapor pressure and the atmospheric pressure are the same. Okay, so the difference between those, the regular boiling point and when it's in solution, is the boiling point elevation. So stirring a solute up in the solution elevates the boiling point. You have a little mathematical formula of this where Kb is the modal boiling point elevation constant, and that's the constant for whatever liquid we're dealing with here. The different solutions, the different solvents will have a different Kb, but the M represents the molality, right? We get the molality by dividing the moles of the solute divided by the kilograms of the solvent. Okay, so remember what molality is. So it's just a pretty little simple formula, and I'll do an example here in a minute. These are some of the Ks, the KBs for the boiling points for water, ethanol, chloroform. So you'll probably have to, I forget what these are in the book, but you'll have to reference these in your book to do some of the problems you have on the WebAssign because they talk about different things that have stuff dissolved in them, what the boiling point elevation and freezing point depression. We're going to talk about that here in just a second too. So the same thing happens the other way. It says they have, when you get to the freezing point part, they want to, when we have normally have freezing point, the inner inner particle attractive forces, they come together. The kinetic energy is low enough that those inner molecular attractive forces can get together and be solid and attract each other. But if we have all this solid in there, then they interfere with that, and you have to have less. You have to lower the freezing points. You have to take more energy away because those solvents, the solutes, I mean, interfere with that freezing process. So you get a lower freezing point than a pure substance. So solid particles interfere with the attractive forces among the solvent particles, and the freezing point depression is given by this similar formula to the boiling point elevation. And this Kf is the freezing point depression constant. It changes wherever liquid we're dissolving in. And M is the molality again, the moles per kilogram thing. Okay, so you have a table of freezing point constants, freezing point depression constants, and this is the numbers for these different solvents. Okay, so you have a question like this. I got this off the WebAssign where the boiling freezing points of a 0.615 molar aqueous solution of non-volatile, non-electrolyte solute. Okay, so that's a typical solid where we can use these KB things, okay, or the KF things. So this is a review of the formulas, right? So we need to find the KB. They gave us the molarity already, the molality, I mean, molality already, so we just need to figure out what this K is. We can figure out how much the boiling point went up, and we can forget the K for this. Well, it doesn't say. What is aqueous solution? What is that? Well, aqueous always means water. Okay, so we just have to look up the Kb for water and the Kf for water. So it says aqueous solution is talking about something dissolved in water. Okay, so this is how you would get the new boiling point. This, I looked up the Kb for water is 0.512 multiplied by the molality, and I get 0.315. So the new boiling point is 100 plus 0.315. So it's 100.315. You have to have whatever you get for this difference in the new boiling point, you have to add it to what the original boiling point was. In this case, we're dealing with water, so it's 100.315. Freezing point, same thing. I got the Kf from the book, multiplied it by the molality, got a freezing point depression of 1.41. Water freezes at 0, so when I subtract 1.141 that, my new freezing temperature, excuse me, is 1.14. So that's why they put salt on the roads in the mountains, right, to lower the freezing point somewhat. So salt dissolves in water. It creates it makes it harder for the water to freeze. So it lowers the freezing point, so the roads takes a lower temperature for the water to actually freeze. Osmotic pressure is the diffusion of a solvent through a semi-permeable membrane. Okay, so we have dilute solution over here, and this membrane is small enough that it will allow the water to go back and forth through it, but it will not allow the solid to go through. Okay, so that's what it means by semi-permeable. The water can go back and forth, but what's in solution, the solute cannot. So if you have this situation where you have a dilute solute on one side and a more concentrated one on the other side, the water is going to go to the more concentrated. It's going to go from the less concentrated to the dilute to the concentrated to kind of even this concentrations out. So that's what happens when it's osmosis. It goes through and the water goes through, but the solutes stay in their respective things. Under reverse osmosis, you may have heard of reverse osmosis things to purify water. What they do is the opposite. They create under pressure, they actually force the water molecules to go from the concentrated side to the less concentrated side. So they leave all the solutes behind, all the salts and anything dissolved in there, and they get the pure water on the other side of that. So it creates a purified water by leaving all the solutes behind, but you have to have a higher pressure on this side to force the water through and leave the solutes behind. Under equal pressure situations, the water would naturally diffuse from one side to the other to go from the dilute to the concentrated side. Osmotic pressure that have moved from one side to the other. Okay. Oops. So, okay, so that's the end of the slideshow.